Welcome to The Explainer. Today, we're diving into a truly fascinating piece of collaborative research from the University of Alabama, Oak Ridge National Laboratory, and Purdue University. They've essentially figured out a way to bridge the gap between hypersensitive quantum sensing and the standard telecommunications tech we use every day. Now, if you follow the quantum mechanics space, you already know that scaling these systems up is just a massive engineering headache. And a lot of that comes down to the physical limits of the actual hardware we use to control them. But as you'll see, this paper offers a brilliantly elegant solution.
It really boils down to this one question. How do you actually talk to a quantum sensor without completely melting it? That right there perfectly captures the core paradox we're dealing with in modern quantum hardware. On one hand, we have these amazing, incredibly precise nanoscale sensors that can pick up the absolute faintest shifts in temperature or magnetic fields. But to actually use them, to talk to them and control them, we traditionally have to blast them with microwaves. And the tools we use to deliver those microwaves, well, they run incredibly hot, which is obviously a huge problem when your quantum sensor needs to operate in an environment that is sitting at practically absolute zero.
So, here's our quick agenda for today. First, we'll look at quantum sensors in diamond. Then we'll break down the microwave heat problem. After that, we'll explore beaming microwaves on lasers, prove the photonic link with some real data, and finally wrap up with a look at a cool quantum future.
All right, Section 1. Quantum sensors in diamond and meeting the NV center.
Okay, so a nitrogen vacancy, or NV center, is basically this tiny little point defect trapped inside the super-rigid carbon lattice of a diamond. But we don't look at it as just a flaw. It's actually an optically accessible spin defect. What that means is, if we shine a 532 nanometer green laser right onto this tiny defect, we can initialize and read its electron spin state. This effectively turns a tiny flaw in a diamond into a wildly precise sensor, one that can measure magnetic fields, electric fields, and temperatures across scales ranging from a centimeter all the way down to a nanometer.
To put that into perspective, when we hit the NV center with that green laser, its ground state becomes optically polarized. But to actually manipulate that spin state, to flip it so we can use it as a functioning sensor, we have to drive it with a very specific resonant microwave frequency. At zero magnetic field, that's right around 2.87 gigahertz. When that microwave hits resonance, the spin flips, the diamond physically emits slightly less red light, and we can detect that tiny dip in brightness. This whole process is what we call optically detected magnetic resonance, or ODMR. Traditionally, to get those 2.87 gigahertz microwaves all the way down to the diamond, we've had to rely on standard coaxial setups.
Which brings us to Section 2, the microwave heat problem. This is our thermal roadblock.
The researchers put it perfectly in their paper, stating that the scalability of the RF delivery needed to coherently drive spin transitions remains a substantial thermal engineering challenge. Basically, delivering microwaves directly to a delicate quantum sensor using conventional copper cables introduces massive amounts of thermal noise and electromagnetic crosstalk. When you're trying to measure incredibly fragile microscopic quantum states, shoving a noisy, heat-generating cable into the mix completely ruins that delicate environment.
Think about it like this. A lot of cutting-edge quantum experiments, things like sub-Kelvin scanning NV microscopy, require ultra-cold cryogenic temperatures. Standard coaxial cables are essentially just heavy metal wires, so when you drop them into a freezing sub-Kelvin environment, they act like leaky hot pipes. They literally pump heat straight from the room temperature lab equipment outside right down into your freezing quantum setup. It is honestly like running a space heater inside a deep freezer. It's a huge physical bottleneck holding back how far we can scale spin-based quantum architectures.
Let's move to Section 3, beaming microwaves on lasers. Enter the RF over fiber, or RFOF, solution.
So the researchers came up with an absolutely brilliant workaround. Instead of forcing a microwave signal down a heavy, hot metal cable, they made the microwave signal hitch a ride on a beam of light. It works in 4 straightforward steps. First, you just generate your microwave signal like normal. Second, you use an electro-optic modulator, or EOM, to modulate that microwave signal directly onto a continuous wave 1310 nanometer laser. And fun fact, that just happens to be a totally standard wavelength used all over the world in global telecommunications. Third, you transmit that laser light through a hair-thin optical fiber. And finally, right next to your quantum sensor, a high-speed photodiode catches the light and instantly converts it back into the exact radio frequency tone you need to drive the spin.
When you compare this directly to the old way of doing things, it's like night and day. Coaxial cables are physically heavy, they're highly thermally conductive, they create electromagnetic interference, and they bleed off a ton of signal power at high frequencies. But RF over fiber? It uses incredibly lightweight glass fiber that gives you complete thermal and electrical isolation. We're talking practically zero noise or crosstalk. Plus, optical fibers can carry massive bandwidths over super long distances with almost no signal loss. It's a real game changer.
All right, Section 4, proving the photonic link, the data.
Because, an elegant theory is great, but we absolutely need the hard data to back it up. If we look at the baseline measurement they took using a standard coaxial cable, you can see the microwave frequency mapped against the light intensity coming out of the diamond. See those deep dips in the lines? That represents the ODMR contrast. That's our visual proof that the microwaves are indeed manipulating the quantum spin state. But here's the catch. To get that deepest dip and 11% contrast, they had to push 25 dBm of power through the antenna. That is a ton of power, which means a ton of heat. You can also see that as the power goes up, the dip actually gets wider, which is a pesky little phenomenon known as power broadening.
Now, switch gears and look at the RF over fiber system. Even running at a drastically lower recovered power of just -0.7 dBm at the antenna, the photonic link still successfully controlled the spin states. You can see the sharp, clear dips right near 2.90 GHz, giving us an ODMR contrast of greater than 2.2%. They even ran a magnetic field sweep to prove that the RF over fiber link tracks perfectly with the changing Zeeman splitting of the quantum defect. The light beam essentially did the exact same job as the old, heavy microwave cable, but it completely isolated the system from the heat. No way, right?
Let's talk about a really crucial number here to quantify this success, 1.81%. That is the optical to RF power conversion efficiency the team hit at 2.90 GHz. Basically, it's the ratio of the optical power hitting the photodiode to the actual microwave power recovered and delivered to the antenna. Now sure, there's absolutely room to improve that efficiency down the line with better modulation depth and higher optical power handling, but hitting this 1.81% benchmark is huge. It completely validates the architecture and proves beyond a doubt that a standard telecom laser can reliably reproduce the precise spectral signatures we need for quantum control.
Which brings us to our final section, Section 5, a cool quantum future, and how we actually scale this network.
By proving we can finally decouple our hot, noisy microwave generators from our freezing, sensitive quantum sensors, this research literally kicks the door wide open for massive scalability. Because optical fibers simply don't carry heat the way copper does, this paves the way for high-field quantum experiments where frequencies jump way up into the multi-10 GHz or even sub-terahertz range, frequencies that traditional cryogenic cables just fall apart on. It gives us that absolutely crucial electrical isolation for ultra-low noise environments. And maybe the coolest part? It sets up a highly stable architecture for sprawling, multi-node quantum networks, where entangled sensors could be kilometers apart, connected entirely by the optical fiber infrastructure we already have in the ground today.
So we've seen today how blending everyday telecommunications tech with cutting-edge quantum physics can solve a massive real-world thermal engineering problem. But it definitely leaves us with an exciting thought to ponder. If fiber optics can essentially cool down our quantum sensors and stretch their capabilities into extreme magnetic fields, what other limits of the quantum world can light help us break? Thanks for hanging out with me on The Explainer today.